So here is a ridiculously fast intro to multi-wavelength light with a special focus on infrared light. You probably know there's many different kinds of light, and in fact, visible light, which is all we can see with our eyes, is really just a tiny fraction of the amount of electromagnetic radiation that is around us all the time. You may be familiar with X-rays, because X-rays help you diagnose whether or not you've broken a bone or have a cavity in a tooth. Here are pictures in the visible light on the left and ultraviolet light on the right. What are these people doing? Whatever they're doing is appearing black in the ultraviolet. What they're doing is putting on sunblock. And in the pictures in the UV, you can see that the sunblock is doing a really good job blocking the ultraviolet light. In order to do good astronomy, astronomers must use all the different kinds of light that they have access to in order to understand the nature of the objects that are emitting the different kinds of light. Here I have the same galaxy in many different wavelengths. In the X-rays, you might use a spacecraft called Chandra. In the ultraviolet, you might use a spacecraft called Galax. In the visible, you might use HST. In the near infrared, you might use an all-sky survey called TUMAS, which was done from the ground, or Spitzer. In the far infrared, Spitzer or Herschel, which are both spacecraft. So in X-rays, the kinds of light we're looking at has a wavelength of maybe 2 nanometers. A nanometer is a billionth of a meter. And we're looking at things that are characteristically quite hot, like 1,000,000 Kelvin. Those are typically associated with black holes of some sort, such as black hole accretion disks, and typically magnetic fields are involved as well. In the ultraviolet, the kinds of wavelengths of light we're looking at is maybe 200 nanometers, or about 15,000 Kelvin. These are typically the hot stars, which are often the young stars. So look at the differences. You can still see this sort of tadpole-y shape in both the ultraviolet and the X-rays, but the X-rays sort of have a halo of matter and some point sources in them. The UV has many more point sources following that tadpole. In the visible, the kinds of wavelength of light is maybe 500 nanometers, which is half a micron. A micron is a millionth of a meter. And the kinds of temperatures of these objects is maybe 6,000 Kelvin. And those are typically the run-of-the-mill stars, like our sun, all ages. So here you can see there's definitely some bright spots in the tadpole, but also some dark regions. It looks very different than it does in X-rays or UV. In the near infrared, you can see definitely clumps of things along this tadpole. And the kind of light we're looking at is about 1,600 nanometers in wavelength, or about 1.6 microns. And the temperatures are typically about 2,000 Kelvin. And these are usually the very cool stars, which are usually the old ones. In the far infrared, you can see there's clumps, but then more diffuse stuff as well. The kinds of wavelengths are maybe 100,000 nanometers, which is maybe 100 microns, and the temperatures are maybe 30 Kelvin. So this is often the cool dust that's heated by the hot stars. So at IPAC, we love infrared. So we like to look at the electromagnetic spectrum this way. We are super focused on the infrared. So in the visible light, here I have a little dog on the left. And there's the picture in visible light, and here's the picture in infrared light. So there's two super important things to note. One is that this is a remapped color image. We call it remapped color rather than false color. Is it false color? Sounds like we're trying to pull something over on you. But remember, your eyes don't see infrared light. So if I made a true color infrared image, this is what you would see, which is not so helpful. So what we're doing is we're taking the wavelengths of infrared light and turning them into optical light that we can see with our eyes. And the way that we're going to do that corresponds to a temperature scale. So in this temperature scale that I've established here, black and purple are cool, red and yellow and white are hot. So you can see his water dish here is cool. You can see the halo of fur around his face is cool. You can see his ears are warm. His face is warm, but because he's a healthy little dog, his nose is cool. So now we know that hot things glow in the infrared. There's a common bathroom sink with the water on. Which one is the hot water? The bottom one. You can see the base of the faucet heating up and the basin heating up. Even when the hot water is on, the base of the cold water faucet is still cold. Here you can see the basin cooling down from the cold water. So infrared can also reveal things that are hidden in visible light. Take a minute and think about what you think that's going to look like. I can tell you the hairdryer is on. There it is. You can see the heating elements in the hairdryer, and you can even see the turbulence in the air coming out. Infrared can also see through some things that are totally opaque in visible light. Here I have just a regular green garbage bag that you might put yard waste in, and you can see straight through it in the infrared. It turns out you personally are really, really grateful for this property of infrared light, because if you are unconscious in a burning building, infrared is how the firemen are going to find you. Firemen all over the country own infrared cameras specifically for this reason, because if they're trying to find people who are unconscious in the smoke, looking with your eyes doesn't help. Once you know that the fireman is standing here on the stairs, you can see his helmet there, but he's really hard to see unless you know he's there. And with the infrared, you can definitely know that he's there. You can see that he's got a rebreather and probably a cooling apparatus strapped to his back. I bet that gear is plenty hot, because where there's gaps in the gear, you can see the heat escaping. Some things that are transparent and visible light are totally opaque in the infrared. Here's a set of French doors in my living room. This door is closed, this door is open, and in the optical you can see through no matter what, whether there's glass in the way or not. But in the infrared, you cannot see through the glass. And this is why when you park your car in the sun in the summer, you cannot touch your steering wheel, because all the optical light comes through the glass, heats up your car, and the infrared then can't get out. And so it just heats up and heats up and heats up until everything in the car is really, really hot. So the next time you get into a hot car, think of all the infrared light that's trapped in your car. There are lots more infrared world photos online. You should Google Cool Cosmos. It's got a lot of different photos, photos that have a slider so you can slide in between the visible and the infrared. And if you dig a little bit deeper, you can find a larger archive of photos, things like a burrito before and after being microwaved, a car before and after being driven, a ball before and after being bounced. Lots of good stuff. So the pictures to this point have been things that you might encounter every day, but now we're going to introduce things that are slightly out of the ordinary on our way to doing astronomy. So what I have here is what astronomers call a dewar. It's really just a fancy name for a thermos bottle. There's liquid nitrogen in there, and the liquid nitrogen is so cold at 77 Kelvin, the camera just gives up and says, okay, well, it's colder than I can see, and just colors it black. Now I'm going to add some frozen peas into the liquid nitrogen. And even though the peas are cold, they are still warmer than the background. And this is what is going on in space. The things that we're looking at are cool, but they're warm compared to the background, and so we can see them glowing in the infrared. There's a familiar constellation, Orion, and there it is in the infrared. How much you miss if you stick just with visible light. You can see the fuzzy patch in the sword is a huge complex of star formation, and there's star formation going on associated with this as part of Orion's belt. There's a big circle around Orion's head, and big circles are often indicative of an explosion of some sort that went off some time ago. So infrared really is where it's at. The different kinds of wavelengths of light that might be called infrared range from about 1 micron to about 1,000 microns. And the near infrared, the definitions between near and mid and far and even infrared and microwave are a little bit squishy, and sometimes depends on who's talking and how the radiation was detected in the first place. But roughly, near infrared is about 1 to 10 microns or so, 8 microns. Mid-infrared is 8, to 50 microns or so, and the far infrared is the longest wavelength. So the kinds of sizes of things that are comparable to the wavelength. So in optical light, which is maybe half a micron, a single bacterium is about the same size as the wavelength of optical light. In the near infrared, the wavelength of light is comparable to a smoke particle or a pollution particle. In the mid-infrared, the wavelength of light is comparable to the width of a human hair. In the far infrared, the wavelength of light is the size of a salt grain. So we're getting into measurably large wavelengths here. Why do we need to go to space to do this? Well, 2 really big reasons. One is that the atmosphere absorbs infrared light, and the other is that space is cold. So for the first point, here I have transmission as a function of wavelength in sort of rough cartoony fashion. So if you are a gamma ray astronomer, an X-ray astronomer, or a UV astronomer, you absolutely have to get up above the atmosphere, because the atmosphere absorbs essentially all of the celestial gamma rays, X-rays, and ultraviolet light that come down from these celestial objects. The visible light does make it, of course, all the way down to the ground. And if you pick your site very carefully, and you pick your wavelength very carefully, and you get to a very dry place, and you have a really good dry night, you can observe in some of these infrared bands. All of these absorption lines are caused by the carbon dioxide, carbon monoxide, water in our atmosphere. So it's good that they're there, because we obviously need oxygen and water, but makes it really hard to do infrared astronomy. You can do some from the ground, but you have to be really careful about what you pick. In order to fully access all the wavelengths of infrared light, including the longer wavelengths, you have to go to space. You have to get up above the atmosphere. Radio light, of course, does make it down to the ground, and there are radio telescopes that observe from the ground. The other big reason is, of course, that space is cold. So if we're measuring tiny bits of heat, it's really tough if your telescope is the same temperature as the air around you. The best analogy I can come up with is observing in the infrared from the ground is kind of like observing in the optical with a telescope made out of those fluorescent light tubes that are on, that your telescope itself is glowing. And so you have to use special approaches to try to get rid of the background from the telescope, from the air, from the warmth around us, in order to tease out the radiation that's coming from the astronomical sources. So, in summary, there's many different kinds of light, and to do good astronomy, you really need to access as many different wavelengths as you can to understand the nature of the objects that you're studying. And it's certainly true that IPAC really is focused on the infrared. Infrared can be done from the ground if you go to a very high, dry place, but to get all of the infrared wavelengths, you really do have to be in space. The next talk in the series will be all about WISE, which is just one of the infrared telescopes.